Hi everybody, thank you for dialing into this webinar. I'm thrilled to be presenting this with Assistant Professor Andrew Ault as the main act. He's from the Department of Chemistry at the University of Michigan. I'm Dr. Mustafa Kansas. I'm the Director of Product Management and Marketing at Photothermal Spectroscopy Corp. Today's webinar title is Particle Analysis with Submicron Infrared Spectroscopy and Simultaneous Raman. We'll be covering microplastics, fibers, and atmospheric aerosols. A couple of points before we get into the meat of the webinar. This will be recorded, so I'll be sharing a link after the event. So if anybody wants to pass it on or watch it again, they can. Also, any questions that pop up through the event, please type them into the box on the screen, and we'll endeavour to answer them at the end, time permitting. If not, we'll get back to you via email. So, really, without any further ado, I want to take over this first part, roughly about a half, and then I'll hand over to Professor Andrew Ault at the halfway point. So the outline today, really, I'll take you through O-PTIR microscopy and its known current limitations. I'll then introduce the Optical-Photothermal IR technique, and then I'll take you through a range of examples with the theme of the webinar in mind before we hand over to Andy Ault to go through the main part of the webinar. Right, so getting into it, infrared microscopy and spectroscopy. Well, infrared spectroscopy essentially is the study of how infrared light interacts with matter. It's pretty simple, and the infrared light excites specific vibrations within the molecule. On the screen there, we've got a spectrum of nylon, so the infrared light excites the various bonds, NaCH, CO, and so on. And infrared spectroscopy has been used for decades. It really is a workhorse analytical technique that covers a whole host of application areas, from polymers through to forensics, life science, environmental now, especially with the particles, aerosols, and microplastics being added to that growing list as well. Though it's been around and it is quite a mature technique, it has hit its limits in terms of what it can do. Primarily, things like limited spatial resolution. We are working with long wavelengths in the infrared. We're in the sort of 7 micron, 10 microns plus. If we look at an image in the visible, it's nice and sharp. You take the same image in the infrared, it starts getting blurry. That's to be expected. And after all, the wavelengths are relatively long. That's what determines spatial resolution. The other one is complex sample preparation. Ideally, you want your samples to be thin so that light can transmit. It gives you the best quality spectra. That means cutting them thin by 20 microns thereabouts. But you just can't cut everything that thin, or it's very difficult to cut things that thin sometimes. Right, so a lot of people also use micro ATR, which gets across some of these, but it requires intimate contact with the sample. It requires precise targeting of the particular particles in particular, and if you make contact with a loose particle, quite often it can move, and you won't know until the end of the measurement. If you're using the same ATR for multiple contact points, there's risk of cross-contamination. The ATR tips themselves can be damaged, cracked, broken, stretched. They're expensive. And of course, there's risk of sample damage or damage to the sample itself. And in this picture, we see how the tip of the ATR there's been multiple contacts, and that's left a trail, almost like a snail trail along the sample there, so indentations are actually changing and deforming the sample. But perhaps one of the more important ones, and I think one of the perhaps least appreciated, is these dispersive and scatter artifacts. Here I have a spectrum of PMMA, the thin film measured in transmission. Spectra look great, nice flat baseline, sharp peaks, nice band shapes. To take the exact same material and make it into a 15 micron bead and measure in transmission again, it's a different story. You've got these weird baselines, you've got splitting of these peaks, peak shifts. You make it a 10 micron, things different even more. The peak shifts are different yet again, and so on as the bead gets smaller. So you can see that with increasing or with changing the shape and size of your particles, you get distorted spectra, which is not what you really want. You want to be able to rely on the spectra independent of shape and size or surface roughness. Right, so we get over all of those really with optical photothermal infrared, O-PTIR. O-PTIR can be described as a pump probe optical spectroscopy technique. The pump, which is what excites the sample, is an infrared laser, commonly a QCL, quantum cascade laser, and the probe is a short wavelength visible, sometimes a near infrared 785 laser. We deliver submicron infrared spatial resolution using O-PTIR, so it's very much like a Raman microscope in that sense. The spatial resolution is equivalent to Raman, but you get all of the richness of the infrared spectral information. Even though we operate primarily in reflection, I mean, we can operate in transmission, but primarily reflection, we end up with transmission-like, quote-unquote, FTIR spectra. So the spectral are clean, no distortions, no scatter artifacts, no interference fringes, and so on. It's not contact, so that minimizes sample prep, and the spatial resolution is infrared wavelength independent. Right, so how does it work? Take you through it. So it all really starts with the infrared light coming and the green visible light, probe light coming through the objective. It's a pulsed source. Being infrared, the diffraction limit is fairly large at 10 microns. But the collinear visible beam can focus much narrower. It's about 500 spot size. And as the sample absorbs that, you get localized heating that changes refractive index sample deformation. So that changes how the green light is scattered. So we measure the green intensity as we're tuning our infrared wavelengths, and that's how we end up with what is essentially a pure absorbance spectrum. Like that. Now, I'll take you through a few key differentiators of O-PTIR relative to FTIR, and even some of the emerging QCL microscopy, direct microscopy type of techniques. Right, so firstly, we obtain submicron resolution, which is Raman-like, but with infrared information. We operate in reflection mode, so there's none of those typical dispersive scatter artifacts that you get with those other types of techniques. There's no infrared detector. Everything ends with the pump, so we pump in the infrared, but we measure and detect in the visible. We're using visible detectors. There's no need to microtome thin slices. We can work from even under 100 nanometers thickness up to as thick as you can fit into the microscope, which is about 16 millimeters. We can work in glass or even other visibly transparent substrates, and we can, perhaps one of the biggies is that we can collect infrared and Raman simultaneously from the same spot, same time, same resolution. In this slide, I want to take you through a couple of what I think are key attributes of any microscope and how traditional IR system compares, and Raman, how they compare amongst themselves. Right? So if you're doing microscopy, typically spatial resolution is important, and if it is, you're more likely to be using Raman than a traditional infrared, so given that a green. If you're worried about fluorescence interference, well, you're not going to do Raman, you're probably more likely to do IR. Spectral sensitivity, Raman is known to be a fairly poor sensitivity technique. IR is pretty good in that sense, and that also correlates to the speed of measurement. In terms of extensiveness of libraries and spectral interpretability, well, the infrared is really rich from the interpretation standpoint, but also from the library standpoint. There's typically about 250,000 odd commercial libraries available, about a tenth of that in the Raman, so they give it a red and green. Reflection mode works best in Raman, doesn't work so well in IR. Water vapor isn't an issue in Raman, but it is with IR, similarly with solvent, water solvent. And it's also similarly with glass substrates, and also with the wavelength independence of spatial resolution. Right? So if you look at that, you can see why labs have one of each, depends on what's important for that particular experiment. If it's resolution, you may go for Raman. If it's spectral interpretability, you may go for IR, and so on and so forth. But imagine if you could, for a moment, take the best of those instruments or those attributes and put them into a single platform. Well, that's kind of what's happened here with O-PTIR, and we do that with the Mirage microscopes. It really does literally combine the best of IR and Raman into one platform. Of course, there's still room for Raman because there are certain sample types that only work best, that only work with Raman or work best with Raman. So that's where the addition of Raman is still very beneficial. So just to prove to you that the reflection-based spectra we collect with O-PTIR are equivalent to FTIR transmission spectra, here are some comparisons. In red here so the red spectrum in the upper right is polystyrene from the library, black is from O-PTIR, so that's considered a perfect match. Same with PET and PMMA. It's worthwhile pointing out that the black O-PTIR spectra were collected on a thick block, probably a few millimeters, and the red spectra were all off thin sections measured in transmission. So they are really equivalent. We talk a lot about spatial resolution. It's important to remember that spatial resolution is a function of your probe wavelengths, as well as the numerical aperture of the objective, and that's approximated with the Rayleigh criterion, which says it's 0.61 times your wavelength in microns divided by the NA. And I've plotted that on the left-hand side as well. If you think about a regular FTIR microscope, or even some of these emerging QCL microscopes, because the probe wavelengths are span across the infrared, you have this exponential function. So in the fingerprint region, which is the most information rich, your spatial resolution is at its worst, it's coarsest. It can be up to sort of 12 odd microns if you're thinking about the 1000 wave number spot. If you contrast that with Mirage, since we work with a 532 nanometer laser, that's 0.532 microns, and use a high NA objective, well, our theoretical resolution is about 416 nanometers, and importantly, it's flat across the entire region. Right, so that's about a 30x improvement, and again, it's also very Raman-like. One of our key value propositions, and what I think excites people the most, is the fact that we can now do infrared Raman in the one measurement with the one click of a button, and provide a submicron simultaneous collection. So it's same spot, same submicron resolution at the same time. It takes advantage of the complementarity that we've been taught about and heard about as it relates to how infrared and Raman work together. It's also confirmatory. So I consider that being that the IR can confirm the Raman result and the Raman can confirm the IR result. It's a single instrument, so you don't have to take your sample from one instrument to another and then not be able to find the exact same spot. It's more sample. It's a more thorough characterization of the sample without a doubt. And now we've recently introduced the option of a 785 Raman probe for any of the samples that have fluorescence on the Raman side. Of course, for the O-PTIR measurements, fluorescence isn't an issue, whichever wavelength of laser we use. I'll take you through a few examples, sticking to the theme of the webinar. Of course, there are lots of great examples in life science and another field, but for this particular webinar, I'll stick to the theme. Before I do that, I want to highlight publications on the rise. This is something I'm really excited about. I've got a link in the bottom left-hand corner to our website where we list our publications. In the first year or two, we had basically 1 or 2 publications a year, but in the first 6 months of this year, we've had something like 11 or 12. And then by the end of the year, I expect that closer to the low 20s, and then I've no doubt that'll explode exponentially afterwards. So I do encourage you to have a look at our website and see who's been doing what with the Mirage. But the first example is a polymer laminate. It was a section that was cut. It's not thin, so it's a flat cut on a otherwise thick film. Drawing a line of 100 nanometer steps, which were performed. We can see the spectra are high quality and lots of differences, even though there were only 100 nanometer steps apart. We can quickly identify that there's a 1462 peak, which is the key differentiator. So if we do some single frequency imaging and ratio those two peaks together, it really highlights that there's a very thin 1.6 micron layer in the middle of EVOH. So this is all in the infrared. We're measuring 1.6 layers, or 1.6 micron layers rather. This is courtesy of IKK, the Leibniz University in Hanover. Another cool example here is some surface contamination on glass. Remember I said before we could use glass? Well, here's the proof. So these are some defects on glass. Some very strong organics on there. You can still see a bit of a broad baseline, which is from the glass itself, but there's lots of organics superimposed on top of that. Picking a couple of bands here, we can do some single frequency, which also highlights that the contamination is quite heterogeneous in itself. Here's some simultaneous IR and Raman on single 900 nanometer polystyrene bead. perspective in terms of mass, that's about 400 picograms that we're measuring here. So the measurements on the clean substrate and the measurement on the bead. The top two measurements are Raman, bottom two measurements are infrared. We've got one for the substrate, one for the bead, and same here in the O-PTIR. So you can see when you're off the bead, it's a flat line, it's featureless. When you're on the bead, you see all of the characteristic features that you expect for polystyrene in the infrared and in the Raman. Also, another example here of other types of particles measured at points A, B, C, and D. These spectra are collected simultaneously, the IR and Raman. The A is clearly a strong starch component. B, we see has some starch and protein, some more protein in C, and then D is purely nylon. So you can see, even though they look similar, it's got the characteristic sharpness of nylon. In the Raman, being a bit more bulk specific, in this case, a confocal aperture wasn't used. So we see less differentiation with these sort of layered structures, but nylon is quite distinct. It's interesting also to note that the glass substrate contributions as well. Fibers. If anyone's ever tried to measure fibers with infrared, you know it's a non-starter. It's a futile exercise. It just doesn't work. But here, it always surprises me whenever I show this. Here we've got some PET fibers, 20 microns wide in this case. In this case, this was some fabric softness study looking at coatings on the fibers, looking to see how homogeneous or not these are. And you can see point spectra taken along the length. Spectra on the left-hand side are raw spectra. These are as is, so there's no corrections, no modifications otherwise. We can see PET across the board, but you can see these additives, these arrows are changing along the length. Less in the right-hand side, but more on the left-hand side. So that's pretty impressive, but it's even more impressive when you see that we can actually collect equal quality data of 800 nanometer fibers. So we've gone from 20 microns to 800 nanometers, and the spectra are unaffected. And so quality spectra, no artifacts, no processing. So another great example here of polymer dispersion, more really an exercise to demonstrate spatial resolution. But moving in from our visible images, we can see different phases. I've collected images here at two different wave numbers, knowing the components that are in there. And this image, there are only 500. But for maximum resolution, we remeasure at 100 nanometer steps. Some spectra from on and off these hotspots kind of indicate where the chemical contrast comes from differences in these carbonyl peaks. But if we really zoom into this small area here, you can see that some of these smallest features here are 275 nanometers. So we're using infrared light here to see features that are in the 200s of nanometers, all without any contact, without any AFMs and the like. Microplastics, obviously a key element of this webinar, but also a key element of many people's research, what's happening in microplastics. And I was very happy to be involved with this paper. We did some work showing the value of O-PTIR and Raman simultaneously measuring microplastics. And I think it's important because microplastics, there are groups who say infrared is the way to go. There are groups who say we need Raman for the spatial resolution. And when you combine the two together, it just means you have better sample characterization. I think it's as simple as that. So here's some recent examples. We're working with WIMS, Virginia Institute of Marine Science, and we're demonstrating here how on gold-coated carbonate filters, in amongst other glass fibers, it's actually a tricky matrix here. If we target a couple of these, we've got two red spectra here on the left-hand side on this particle and a couple of spectra on the darker particle here. So the red spectra clearly are polystyrene. But it's interesting that the black spectra from the black point here, actually hard to see maybe the black marker there, is characteristic of carbon black. Right now, carbon black in the infrared is featureless, hence in the infrared it's flat. But the Raman really shows that well. So this is a really great example of how the two are complementary. Things that work well in the infrared don't always work well in Raman, and vice versa. Right, and these are the live research results for polystyrene for the infrared. and for the Raman and the Rose high quality #1 hits. This is one of my favorite examples as well, because we've gone through a really difficult study. We've gone with polystyrene beads of varying dimensions from 900 nanometers, 2.5, 2, 4.5, and 10 microns, and we've thrown in a 3 micron PMMA bead. But as if that wasn't hard enough, we've done this in a salt water matrix, and we've then tried that on a calcium fluoride substrate. It could have been glass. And what that means is now you've got these mixtures of beads in amongst salt crystals, and measuring in salt crystals in amongst salt crystals with the infrared. It's a no-no, it just wouldn't work. But in this case, we've targeted various beads. You can see the PMMA beads are all equivalent. So the spectra are the same high quality. The various sized polystyrene beads all look like polystyrene. And again, I'll stress that these spectra are raw, unprocessed. In this case, if we know some of the distinguishing peaks, we can then do single frequency images at those peaks, and the image lights up like a Christmas tree, identifying the location of the various particles. So I'll stress again that the spectra are consistent regardless of particle shape or size. A real-world example here of a microplastic. In this case, there's a little bit of fluorescence background in the Raman. The infrared, of course, is insensitive to fluorescence, so that's nice and flat. And when we run that through a search engine like that from Wiley's Nodal, used to be Bi-Rats, but now acquired by Wiley, it worked really well because we can do the simultaneous collection, and the know-it-all from Wiley can now do the simultaneous spectral searching. So rather than having two separate, one for the IR, we can combine that, or rather they can combine that into a 2D scatter plot, where one axis is the Raman heat quality index, and the other axis is the infrared heat quality index. So of course, anything in the upper right-hand quadrant means it has a good IR match, it has a good Raman match, and it means you can have a lot of confidence in the correct identification of that result. So that's the infrared, and then that's the IR spectra as a comparison there. And so and I'm really happy to also announce that we've got a special partnership with Wiley, where all IR Raman systems have a free 1-year license to know-it-all and access to their entire database for the first year. That brings me toward the end of my section. I think the key takeaways I'd like you to leave with and quickly remember and talk to your colleagues about are really that O-PTIR takes infrared microscopy beyond what I call traditional and accepted limits. It's a mature technique. Remember, it's been around for a while, and we can do certain things, and we're just used to it doing only that and not doing much more than that. Well, we've now leapfrogged beyond those limits, and now we're also combining IR and Raman into a single platform. That's another big element. So it's submicron. What does that mean? It means you see a lot more detail. It's non-contact. There's no cross-contamination. It's easy, lack of sample prep. It's dispersed, so there are no dispersive scatter artifacts which can absolutely kill certain infrared measurements, especially when you're working in reflection mode. So insensitive to sample shape and size. It's really important, especially when you're working with small particles of different sizes. There's also no sample prep, so basically you put your sample in there, point and shoot, and off you go. IR Raman, same spot, same time, same resolution. With that, I'd like to hand over as quickly as possible to our main speaker, our main act here, with Assistant Professor Andrew Ault. So he can talk about his new publication and the work he's done with the Mirage system. With that, I'll hand over to you, Andy. Take it away. Thank you.
Great. Thanks so much, Mustafa, for the introduction and for allowing me to be a part of this call. We're really excited about the work we've been able to do recently with the Mirage, and particularly the system that we have here at the University of Michigan, where we're looking to use the optical-photothermal infrared and Raman capabilities of this microscope. And so just a quick little bit about myself. I'm an assistant professor in the Department of Chemistry here at the University of Michigan, and my research focuses on atmospheric aerosols or particles. Now, aerosols and particles have gotten a lot of attention in recent months due to their connection with infectious disease, but there's many different sources of particles that get into the atmosphere. And so what my group really focuses on is trying to understand what are these particles made up of, and how are they evolving during their time in the atmosphere? Because this has large impacts on both human health, if you breathe these in, as well as climate change. And so today I want to tell you a bit about our recent paper that came out in Analytical Chemistry, where we were able to look at both model systems in the lab as well as real atmospheric particles with a combination of photothermal IR and Raman spectroscopy. And so with that, I'd love to show this video as a highlight as to why we should care about these aerosols. And so if you're able to see this video, what you're looking at is a NASA simulation where each of these different colors represent aerosols coming from a different source. So the pink is coming from different anthropogenic activities. This means fossil fuel combustion, industrial emissions. The more white and blue shades are coming from the oceans. The orange shades are coming from fires. You can see here, this is last December over Australia, when there were these massive forest fires there, and you can see those fires leading to large emissions of particles. Or you can look off the Sahara here and see dust coming off of Africa. We recently had a dust storm come over Miami, for example, from the Sahara. So these are all aerosols. And so the problem with trying to understand aerosol impacts is that measuring the chemical composition of something that is, less than 1/10 the diameter of your hair. Your diameter of your hair is maybe about 50, 60 micrometers. A lot of these are anywhere from are in the order of a couple hundred or smaller nanometers. And so this has been a real challenge for a lot of the measurements that we want to make, because so many spectroscopic methods are limited in spatial resolution when we want to look at something that's a micrometer or so in diameter or smaller. So the work that we do in my group is that we focus on everything from the developing and utilizing methods, including optical-photothermal IR, to try to understand the composition of these atmospheric particles. And so this means, we also have done things in the past with AFM-IR. We've also done just some we could say, traditional Raman microspectroscopy. But we also then use these new methods that we've developed to try to look at, all sorts of different systems. Most of our work focuses on atmospheric systems. That's these two projects in the upper right here. But we also do work looking at indoor surfaces. We have a review coming out in chemistry in the next few weeks, so looking at, say, indoor surface coatings and the impact that that can have on health. We do some work looking at nanoparticles that are incorporated in algal blooms. So we really looked at a wide range of environmental processes, but our focus is always on how can we use new spectroscopic methods to probe this. And so one of the things that we face when we're trying to look particularly in the atmosphere, and this also, I should say, applies to things like micro or nanoplastics as well, but a lot of these things, nanomaterials in the environment, they all have, the most abundant sizes are typically about 100 nanometers or so in diameter. So here you can see I've got an x-axis that's about on meters. So, just for reference, this is 1 micron here at 10 to the negative 6. 10 to the negative 7 is 100 nanometers, 10 to the negative 8 is 10 nanometers. So we're on a log scale, and this is for atmospheric particles. You notice that the most abundant sizes are about 100 nanometers. And there have been many mass spectrometry methods that folks have tried to use for this, and they do provide valuable information. That's what I did my PhD on. But spectroscopic and microscopic med key information that we just can't get from SPEC. When we look at this, we think about what are the methods that we have to try to visualize individual particles. So for years, what we did know of particle morphology and composition, we knew from electron microscopy, scanning or transmission electron microscopy, coupled with energy dispersive X-ray analysis, or EDX. And so we had that, but we also, that only really gave elemental information. Maybe if you used electron energy loss spectroscopy, you'd learn a little bit about the carbon information, but it was pretty minimal. Some folks have done some nice work at beamlines with scanning transmission X-ray microscopies coupled with near-edge X-ray absorption line structure spectroscopy. This looks at electronic transitions, but the problem is that you need a beamline, such as the Advanced Light Source at Berkeley or the light source at Brookhaven National Lab or Argonne, things like that. So you have to go to these sources, and we wanted to be able to look at particles in our lab. So then you have things like optical tweezing, which again is limited to particles much larger than a micron. Raman microspectroscopy is really where I started to get into doing spectroscopic analysis of particles, and that's good down to a little bit below 1 micrometer in diameter, but there's a couple of pretty big limitations, one of which is if you have any fluorescence that can swamp your signal, and we do, and so if you don't have any other sort of complementary method to learn something about the particle, if you're swamped by fluorescence, you're going to be limited in what you can learn. And the other issue is that you're not going to be, it can be a little bit challenging to get to smaller sizes. But so we've always wanted to use IR microscopy in the lab. The problem has been that IR microscopy is pretty limited because of the diffraction limit of infrared radiation to particles, generally larger than 10 or so, 10 or 20 micrometers in diameter. And so if you look at where the most of the particles in the atmosphere are, and you look at where IR microscopy is, you can see that there's a pretty big gap in terms of the sizes that we're able to analyze. And so that's where we want to be able to look spectroscopically at this critical size range for health and climate impacts of aerosols and particles. And so, and we want, when we do this, to be able to get as much chemically complex information as you can from, say, vibrational spectra. So we started working on this back with Asst in 2017. We published a paper in analytical chemistry where we were the first to apply atomic force microscopy coupled with photothermal infrared spectroscopy to look at individual particles down to about 100 or so nanometers in diameter. And this was work by a former graduate student of mine named Gandhi. And we were really excited at that point because, as you're aware from Mustafa's explanation of the method, we're able to look at photothermal expansion of individual particles, and as they expanded, you change the oscillation of the cantilever and you can get an IR spectrum. And so you can see here that we saw pretty good agreement for this particle between a traditional FTIR spectrum, just with an ATR setup, attenuated total reflectance. Here you can see nice modes for the ammonium and for the sulfate of ammonium sulfate particles that we were looking at. And the AFM-IR has very similar modes. And you'll notice we also see the water band there as well. These were liquid droplets we looked at on the AFM. But there were a couple of limitations to this. One of the, and so, sorry, I should mention that we also did things like look at phase separated particles. So here we have a organic coating around a salt core. The salt here in the middle is ammonium sulfate, and the here we have polyethylene glycol as the organic, and we were able to show both the inside and outside in terms of their spectra, which is what you're seeing over here on the left. And we compared this to a much larger particle here. That this one here is a little less than a micrometer in diameter. This one here is 2 or 3 microns that we were able to look at with Raman, and you'll see from the spectra that we were able to really distinguish these two quite clearly. The other thing that we were able to do was to do some mapping, where we could look at, here are 2 particles from the ambient atmosphere that we put on a silicon wafer, and you'll notice they kind of merged together a little bit, but you can see that we could get some pretty decent spectral information. But this was pretty slow, collecting only words at a minimum for each wave number, and so this was, challenged us in terms of being able to have much throughput for our analysis. So we have done things like, upgrade our laser system and tried to increase the speeds, and so now we're able to go to somewhat smaller particles, but we still have been limited by the fact that we have to use a tip, that we had pretty slow spectral acquisitions, and we only had the photothermal infrared information when we were doing AFM with photothermal IR. So what we're really excited about is this paper that just came out in early or mid-June. Nicole Olson, a 4th-year graduate student in my group, was working on this brand new Mirage instrument we have in our lab here at Michigan, and she was able to look at simultaneously do optical photothermal IR plus Raman of atmospheric particles. And so Mustafa's already explained the method in the prior section, but just briefly, we're focused on getting both IR signal by looking at the elastically scattered photons and looking at the change based on the photothermal expansion, as well as Raman's from inelastically scattered photons that have interacted with our system. So, what were the advantages of the optical photothermal IR from our perspective? We were able to get silicon wafer quartz slide, microscope slide that we wanted to. That was very helpful. We worked a lot with somewhat sticky, gooey organic materials, and often this ended up being pretty challenging when we would try to do AFM with them because the tip would drag it all over the place and smear it. It was tough to get really nice mapping sometimes. The lack of that lack of contact was great. The fact we could put any substrate in there for the most part, and I'll show in a few slides that we tested a bunch out in that analytical chemistry paper. We were able to look at particles, atmospheric particles that were actually quite small because when we pulled them into our device for collecting, which is called an inertial impactor, the particle will hit and spread, and so that hitting ends up meaning that even if I had something that was maybe 200 nanometers wide, when it's up in the atmosphere, when it hits and spreads, it's probably going to have projected area diameter of 700 or 800 nanometers. And there we're able to see it with the optical photothermal IR. And that's letting us get closer to these really important sizes for the atmosphere. We're able to do point and shoot measurements, and we were able to do simultaneous IR and Raman, which I will show some data for. And we are incredibly excited about being able to couple both of those. So, and we've also worked with some of these IR databases so far, which have been really nice for identifying features. So that's been a real plus as well. So with the optical photothermal IR, you can see here, I've just shown what some particles, it's an AFM image, just to give an example of what particles might look like on a silicon substrate, which is the one that we use the most. And so with this, there you have the cassegrain, the reflective IR imaging objective. Your photothermal IR source comes in, either from a quantum cascade laser, a QCL, optical parametric oscillator, or OPO laser. And these are letting us look across most of the sort of traditional portions of the mid-IR. But then the key is that instead of using the AFM tip, as we did in AFM photothermal IR, here we're using a laser, a 532 laser that's coming in, and we're looking at changes in its scattering intensity. And so with this, when the particle expands and it changes the scattering signal, that's going to end up being, after the data is processed, you're able to work back from the linear spectrum. And so here you can see really just a gorgeous ammonium sulfate spectrum. We were really excited. This is one of the first spectra we collected. It worked very well in terms of giving us both similar intensities for the ammonium bend we have right here, as well as the asymmetric vibration of the sulfate ion we have. And so those are just the calculations that we've done. And these are well-known systems. Of course, now we're working towards more complicated ones. This is just meant to show an example. But in both cases, the fact that you're having a dipole moment shift ends up giving you a really nice IR spectrum. So if we only had this, we would have been really excited, frankly, because now we were able to look much more quickly. These spectra were a lot faster than the AFM PTIR, as well as have been quite reproducible for us. So because we're using this 532 laser, my lab has used a Raman microscope for years. It's been sort of our workhorse of our lab. And so we've always been kind of bummed that we didn't have the photothermal IR information combined with Raman that we're so used to interpreting. So the great part is that this 532 laser that we're using, this is able to give us, we're able to look at the scattered light, elastically scattered light, and get a Raman spectrum from that as well, either Stokes or anti-Stokes. And so with the Raman spectrum, we're now looking at, say, the symmetric vibration of the sulfate. So here, there's no change in the dipole as our oxygens move in and out from the sulfur, but we do have a change in the polarizability. So that gives us a really nice Raman spectrum, while at the same time, and this is for the same particle at the same time, about a micrometer in diameter, we were also able to get sulfate and ammonium IR features. You'll notice this ammonium mode here is not Raman active, but it is IR active. So if we just had our Raman here, we'd be relying on the NH stretches at 3200 or so, and those aren't very sharp or distinct. So this is a really, being able to look at all of these different modes enables us to look at chemical detail that we wouldn't be able to otherwise. And we're able, because the spatial resolution is determined by this 532 laser, and that the numerical aperture of the objective, we're able to actually look at particles less than a micrometer in diameter, which is pretty exciting in terms of what we're able to look at. So here you can see left here are Raman spectra, and on the far right here, this middle is Raman, and on the far right here, we've got particles impacted on a silicon wafer. And these are just ammonium sulfate that we've chosen to give you a sense of what we can do. And you can see here, this is your classic infrared spectrum off of silicon. We've got the NH and OH stretches out here. You've got your NH band as well as your ammonium sulfate antisymmetric stretch, your sulfate antisymmetric stretch here at 1100. And then in our Raman, we have a very nice symmetric mode for ammonium and the weaker mode for sulfate and a weaker mode for the ammonium out here, about 3168. So we were excited when we saw this, but we said, okay, silicon's great, but let's try out some other substrates as well, just to see what possibilities are out there. And so I already showed you the silicon data up top here, but we also looked at quartz. This is just a quartz microscope slide, nothing fancy. We again got great IR spectra and some pretty solid Raman, although you'll notice a little bit of baseline that we had to account for. We tried it off of a germanium crystal, germanium wafer essentially, similar to the silicon wafers we were using, and again, pretty solid IR spectra and Raman spectra. We also tried it off of a couple of foils, aluminum foil as well as silver foil, and again, we were able to, for all of these, see the ammonium sulfate particles. Here you'll notice these are a little bit bigger, but again, they've hit and spread. In terms of what their diameter was before they hit and did that, these are on the order of a micrometer or so in diameter. So we saw that we could use all these different substrates, but the one that worked the best for us, at least, was just a silicon wafer that we score and break into small pieces and put into our little collection device. So the next thing we did was we wanted to say, okay, that's great that we can look at ammonium sulfate. The atmospheric world cares a lot about this, but how is this going to handle a whole bunch of different inorganic salts and organic compounds, that are important, not just for the atmosphere. And so here we looked at, for example, ammonium nitrate, where you can see both the Raman. We have a very nice peak here for the nitrate mode and the ammonium. And we've looked at these for years, but now we're very excited with the photothermal IR. We were able to see both the nitrate asymmetric vibration as well as the ammonium. And then we were also able to, still get those same ammonium and water features out in the stretching region, or the NH and OH stretching regions that we wanted. Sodium acetate, similarly, we got some really nice CH vibrations here, as well as some of these different CO, C double bond O bends in both the IR and the Raman. And we continued and looked at other things, things like sucrose, which is a little bit more viscous, doesn't spread as much when it hits, sodium dodecanyl sulfate, a good surfactant, and ammonium oxide. So all of these, if you compare these IR spectra to, the databases of IR spectra, these ended up matching really quite well, which we were very excited about. So having both the IR and the Raman information was really important when we wanted to be able to identify what we're looking at. But of course, it's great if I know what I'm making the particle of and I stick it onto, a silicon wafer or whatever. That's all well and good. But what happens when we actually need to look at something that's not just homogeneous mixture? So here you can see we've got an optical image of a particle that we've made the space separator. So we have a liquid aqueous ammonium nitrate core here, as well as a polyethylene glycol shell. And you'll notice this is for about a 5 micron or so particle, but the spatial resolution, each of these pixels here is on the order of just about 50 to 100 nanometers. And so you can see that we had really nice mapping capabilities of the PEG polyethylene glycol shell here, as well as that ammonium nitrate core. And if we went and did a ratio of PEG to nitrate across the particle at each of these different points here, about a micrometer or so spaced apart, you'll notice that they're nicely, we saw, the amount of PEG to, is much higher in ratio to nitrate at the edge, and in the middle we have much more nitrate. And you can see here spectra from both the middle and the shell. And, we multiply the shell times 10 because it's a little thinner on the edge of the shell. So this ended up working really well for model systems, but what happens when we go to the real atmosphere? And so this is where I think where the power of the Raman and IR together is something that's really going to enable us to push our research forward, is that we were able to look at, a particle where before, if we had just done Raman, we just said, okay, here's some nitrate, here's another, maybe the nitrate asymmetric stretch, but we don't have much really to go on. maybe there's MH, maybe there isn't. We don't really have great signal. But when we now are able to turn into optical photothermal IR, we had a very strong ammonium band right here at about 1411, which is right where that should be. And so when we had that, we said, okay, this is an ammonium nitrate containing particle. If we'd have just had Raman, we wouldn't have been able to know that. Similarly, when we were looking at maybe a spectrum like this for the Raman in the past, we would say, okay, we have some organic modes, but we're not so sure what they are. We have, some different CA stretches, bends, CO stretch. But once we were able to look at the IR, we said, oh, wow, we've got a really strong carbonyl here, as well as some other modes that are going to help us identify that organic material. And so we did this for particles over a range of sizes, not just here. I'm showing you some larger ones. Between 3 and 5 micrometers in the atmosphere. But this one, we were able to look it down, in the range of between 400 nanometers and 2.8 micrometers, and we still got really solid signal, and we're able to see some really nice features for these particles. And once again, here in the bottom. So, and sorry, I should say on this last last particle down here, this is a particle. These are particles that are less than 400 nanometers in diameter that we've collected. So we're starting to push the limits of our detection capabilities, but we still were able to get some really nice features that were able to tell us some information about what was mixed before. So the exciting part about what we've been doing is that now with the Mirage, we've been able to bring IR microscopy all the way down to less than a micrometer in diameter. And we're starting to mess with things, before they've even hit the spread. We're able to, really start approaching this. So we've looked at, 400 nanometers is right here. And so I just showed you particles on the last slide that actually are starting to get into this, really deep into the critical size range for health and climate. So the fact that we're able to do that with both IR and Raman simultaneously is something that we're really excited about and think that's going to push our research quite forward. And so I wanted to spend the last minute or two here telling you about some of the work that we do, which is we try to look specifically at what is the pH of some of these really small particles. And so this is from a recent review paper that I was involved with, where we're looking at all the different places that we care about pH in the atmosphere. Cloud droplets, aerosols, all of these different things can have big impacts on the environment and health. And so the challenge with measuring pH in these is that if you have if you look at everything as an average and don't look at individual particles with microscopy and spectroscopy the way we do, you end up missing this story sometimes. And so here, if I put dust particles in, I put 3 that are at pH 6. We're going to assume that they're aqueous, that they've dissolved due to atmospheric acids. Maybe we put in some sea salt particles as well as some haze particles, secondary organic aerosol mixed with ammonium sulfate. We put them all together. And even though I've had, just 3 particles over here and 5 over here, if I look at the pH of the solution, assuming they're all the same size, the solution ends up with a very acidic pH. And so this is why we want to understand particle pH at the single particle level. And so we've developed a number of methods in my lab. We have an acid conjugate base method. We have a calorimetric method based on pH papers, as well as a polymer degradation method that we use. And so these latter 2 were published in Optical Chemistry, as well as we had some work where we were looking at acids and conjugate bases with Raman, and we're very excited now to be able to do that with photothermal IR. These are some of the example papers. Here's our analytical paper where we're showing this polymer degradation. This came out earlier this year in 2020. We've looked at what's called calorimetric detection using cell phones and pH paper, and we've compared this with our Raman, and we hope to with photothermal IR, as well as we've got an acid conjugate base method with Raman that we again are extending now to photothermal IR. So these are all different ways that we're trying to understand aerosol acidity, but microscopy and spectroscopy of the type that we can now do with this optical photothermal IR is really at the heart of what we do for the research in my group, and we're hoping is making a difference in terms of understanding how particles impact aerosol and aerosols impact climate and health. And so with that, I just want to make sure to thank all the members of my group, the great work that they do, as well as our collaborators down here. And thank you all for your attention. It's really been a pleasure telling you about the way that we're using the Mirage, the optical photothermal IR plus Raman, to push our research forward, and look forward to seeing some of the great stuff that some of these instruments in the future. Thanks so much.
Okay, thank you, Andy, for that fascinating webinar. As you've been talking, we've got quite a few questions coming in, so I'll jump into them right away. First question is I think this one's for you, is what spatial resolution have you been able to see?
So one of the nice things about the system is that we've been able to, we can use, we've used it as small as 50 to 100 nanometer step size when we've been mapping, and we've been able to resolve that fairly well, which we're quite excited about. And so some of those phase separated particles with the organic on the outside and the inorganic in the middle, we've been able to see quite nicely down to that 100 nanometer or so spatial resolution.
Thanks, Andy. Actually, that bodes or correlates pretty well with some of the earlier stuff I showed with, say, the polymer dispersions, where I was seeing easily things in the sort of 200 nanometer range.
Great.
Well, another question here. If this one, Andy, if you don't mind, I may take myself. The question is, well, what about colored particles, and does the green affect them? Let me answer this in a general sense. So how do we handle colored materials? Because there's, I suppose, a couple of things. If there's color, they can be associated with fluorescence. And I'll stress again that the O-PTIR channel is completely unaffected by fluorescence. If fluorescence is there, it will certainly impact on the Raman, but not on the infrared. And sometimes color or even dark samples may absorb a lot of that probe beam, so one has to be mindful of how much energy you put on there, and it's a similar thing to, I suppose, with Raman. You have to be careful with how much laser power is delivered. But for those dark samples that can absorb like crazy and hence potential damage, the system has an option to switch to a different detector, an ultra-sensitive APD detector that operates at really low light levels. So with the O-PTIR, you can switch to super low light level, like fractions of a percent of full laser power. That really mean the Raman is no longer useful, but the O-PTIR is compensated by switching to that lower powered detector. This next one is probably for you, Mandy. The question is the Raman spectral quality similar to a dedicated Raman microspectrometer?
Yeah, I was actually, and I will admit I was not 100% sure that it was going to be, but we've actually been very pleasantly surprised in terms of the response. So if we take a sample and we put it under our, sort of Raman that we've had for 5-6 years, and compare it with what we get with the Mirage, the intensity and the spectral resolution have both been very comparable. And so we haven't had to, if anything, we're still able to collect, our spectra. Often on our other instrument, we'll use maybe 3 acquisitions at, 5 seconds or 15 seconds, things like of that order of magnitude. And we're able to do those just fine on the Mirage with the Raman as well. So it's not really slowed us down at all, which we were pretty excited about, and we're still getting the same quality of Raman spectra.
Okay, this one is definitely for you. Have there been any aerosols you have not gotten signal from yet?
Well, that's one of the nice things about atmospheric particles, is that they're often, this tiny 100 nanometer particle, or 200 or 300 nanometer, it typically is going to have hundreds, even thousands sometimes, of different species in one particle. So there's almost always something that's going to give us signal. So no, we have not yet had a case where we haven't had signal. We have had a few that have fluoresced, which was, honestly the end of the road for us when we just had Raman, if that was all the signal we could get. But now, even with those, we've been able to get some really nice photothermal IR spectra. And so that's actually been helping us, before we just would have, a chunk of our pie chart of different things we were, or a fraction that was like fluorescent and we didn't know anything else about it. But now the IR has been able to give us some information about those. So yeah, we haven't really had any particles yet that we just didn't get any signal from. That we've been fortunate, but that hasn't been a thing.
Actually, this next question kind of ties into your answer, and I may elaborate by answering this one, is how is O-PTIR insensitive to fluorescence? And I'll let's follow up with what Andy answered the previous question. The fluorescence rejects, so the Raman channel, you can't do anything about that. If it fluoresces, it upsets the Raman, no doubt. The O-PTIR is insensitive because we use a lock-in amplifier to demodulate the signal. So if you remember the video I had it early on, it showed the infrared pulses being modulated. It was on, off at a particular rate, typically about 100 kilohertz. That means that the green signal that we monitor back, though there's always some fixed level of green coming back, on top of that constant level of green, there's a certain amount of modulated green that's in response to the infrared modulation. So that modulated green is demodulated using a lock-in amplifier, and that removes any fluorescence whatsoever. So as Andy said to the previous question, things that fluoresce in the Raman, you see zero fluorescence in the O-PTIR. And maybe this should be the last question as we're nearing the end. This one is probably for you as well, Andy. How similar are the O-PTIR spectra to the ATIR spectra?
So yeah, we've done some comparisons with not just some of these standard inorganic salts like ammonium sulfate, which turned out to be quite comparable. But we've also started looking at some more complicated molecules. We use organosulfates a lot in our work, and we've done some pretty detailed analysis. And frankly, the modes have all lined up pretty well, which we were excited about. I'm sure Mustafa and others have mentioned, you have to sometimes do some small corrections for chip transitions on the QCL laser or things like this. But on the whole, the modes are where they should be. The peak shapes, there can be some small differences. And I'll admit we're still sort of piecing those together. But I mean, that's true of any method I think you use where you're going to learn some of the nuance. But overall, the peaks are where they should be. And the ratio between the different peaks, in terms of their intensities, are where they should be. So it's we haven't had anything where we said, wow, this is just a completely different spectrum on the photothermal IR compared to the ATR, which we worried about, but that hasn't been an issue, which we've been pretty excited about.
Okay, I think I'll then close this up for questions. Once again, Andy, I really appreciate your time and effort. It's great to see these papers coming out. So I love hearing our researchers talk about how they're using the Mirage technique to further their own research, and hopefully this will just expand the field and expand the interest in this emerging technology. One more time for our attendees, this is a recorded webinar, so I'll be sending out a link to be able to watch it or pass it on to your colleagues. And any questions that we didn't get around to, we'll get back to you as soon as possible via email. And with that, I want to thank everybody for their taking time out of the day to come and listen to this webinar. I hope you've learned something new, and visit us at our website and email us with any further questions or interests. Thank you, and wish everybody a good day. Bye-bye.